So you clicked on this video because you want to understand the derivation for the ideal gas equation. I can't just talk to you about it. You need to watch the tutorial video. It's longer than most tutorial videos. It's about 7 or 8 minutes. So I've tried to really break it down and explain why each equation links to the other in the way that it does. So I'm not going to waste any more time talking to you. Check out the tutorial video.
Okay, so let's do something a little bit more complicated. Let's talk about how we're going to derive the ideal gas equation. Okay, so how are we going to do this? How are we going to get here? Right, how are we going to get here? Well, we need to think about the physics of the situation, right? We need to think about how gas particles are actually colliding in a container. They're going to be doing this, right, and then this. They're going to be going here, bouncing off of that wall, and then back here and bouncing off of this wall. So, with this in mind, when these particles collide, we can say that the force that they exert is going to be equal to the change in their momentum over the change in time that happens. Okay. Now, in order to get to here, we need to really break this down into its constituents. Okay. Now, we know that because speed is equal to distance divided by time, we can say that the time is equal to the distance divided by the speed, right? So we've got, this is distance 1 and this is distance 2, right? So effectively we've got 2L, okay, and I'm using L to express length in this particular derivation, and we can say that speed is equal to c, okay, and you'll see why a bit later. So we can say that time is equal to 2L divided by c, right? Time is equal to distance divided by speed. And it's 2L because we've got one collision here, and then we've got another collision here on the way back. Okay, so that's that part. And then we can say that momentum, we know that momentum is equal to mass times velocity, right? That's no problem. So thinking about this, we can say that force is equal to 2mc divided by 2L divided by c. Right, this is one thing. This is here. Okay, and the reason that it's 2mc is because obviously we have got the momentum of this and the momentum of that. Okay, so this is going to be mc and then this is going to be mc. Okay, so that's step 1. And obviously we can do a bit of cancelling here. I mean, that should say L, right, not C. Okay, we can do a bit of cancelling here. We can divide through by c and make this c squared, and then we can also divide through by 2 here, okay, and then that brings us to F equals mc squared divided by L. Okay, so that is our first step, and that's really, I would argue, probably the most important step. But this is the force of one particle, and I'm not particularly interested in the force of one particle. I want to know the force of all the particles in the system, right? Because there's going to be millions of gas particles in this system. So let's do this. Okay. Well, I want to know the average force which is exerted, okay? And that is going to be equal to mc root mean squared. It's going to be equal to the RMS value, because we're talking about the mean square speed of all the particles, right? So it would be c RMS squared, okay? And we're going to be dividing that by L. But obviously I need to take into account the number of particles that are at play, okay? And we're going to call that N. So we say that the average force is equal to N m c RMS squared divided by L, okay? And then we're going to multiply that by 1/3. But why are we going to multiply that by 1/3? Well, the value of a third is used to express the random motion of the particles, okay? Because if we measure the motion of the particles, we can see that approximately 1/3 of them at any given time are moving between 2 opposite faces of the container, okay? So that's what we're using 1/3 for. And then our expression effectively becomes F is equal to Nm CRMS squared divided by 3L. Yeah? Okay, so that is our average force. And now what we need to do is we need to take this and we need to intercalate it into our pressure equation, because really we're interested in the pressure that this whole gas system is exerting, right? So we would say that pressure is equal to Nm CRMS squared divided by 3L over L squared, right? Because area is measured in units squared. And then what we do is we're going to simply do this, divide through by L squared, L cubed, right? And then we're going to end up with P is equal to Nm CRMS squared divided by 3L cubed. Okay, and then we're going to assume that L cubed is equal to volume, and we know that because volume is measured in cubic units, right? So we can say that PV is equal to Nm CRMS squared over 3, which is exactly the same as PV is equal to a third times Nm CRMS squared. And that is how we derive our ideal gas equation. So I suppose the question then becomes the second part, which is to show that the average or the mean kinetic energy of an ideal gas is proportionate to its absolute temperature. And we can do that if we assume the equation. So we know that we've already derived our ideal gas equation. We know that PV is equal to a third of Nm CRMS squared, and that's our ideal gas equation. But we also know that PV is equal to NKT, right? So we can equate the two. We can say that because PV is equal to 1/3 Nm CRMS squared and PV is equal to NKT, we can say that 1/3 Nm CRMS squared is equal to NKT. Get rid of M. I'm not really interested in that. So 1/3 is going to be M CRMS squared, which is going to be equal to KT. Now, what I'm going to do is rewrite this half of the equation as 2/3 times a half M CRMS squared is equal to KT. Okay, and we can do that because 2/3 times a half is equal to a third. And then I'm actually going to keep this half over here, and I'm going to multiply across by 3/2, right? So I'm going to get rid of this, and I'm going to say that half M CRMS squared is equal to 3/2 KT, right? Now, effectively this is EK, right? So we've shown that the average kinetic energy, and it's average because it's CRMS squared, right? It's the average, it's the mean square speed, right, of all the particles. So the average kinetic energy, or the mean kinetic energy of the ideal gas, is actually proportionate to the temperature. And the reason it's proportionate is because 3/2 is a constant, and then K is also constant. K is just our Boltzmann constant, right? Okay, so that's how we show both of those things. Fairly complicated, but I think that it's definitely something that is worth knowing. Okay, if it does come up in the exam, it's worth a good chunk of marks, like 6 marks for the first question, maybe 3 marks, 4 marks for the next one. So these are derivations that are definitely worth knowing when we're studying our thermal physics. Okay, so hopefully that has allowed you to understand that derivation and how it also relates to average kinetic energy. Yeah, you need to know it. It's a fairly complicated derivation, but it's 6 marks in your exam, and if it comes up, you're going to kick yourself if you don't know it, so you need to learn it. In the meantime, like and subscribe, please, share, support the channel, and I'll see you next time. Bye guys.